Hi all. In this segment, I'm going to be talking about some of the applications of the electrochemistry we've been doing. And specifically, we're going to look at we're going to look at some common types of batteries and the reactions they use in order to generate electrical energy. So it'll just be a brief survey. Most of these things are covered in the book. I'm just sort of refreshing your mind and your memory and what's going on. So acidic dry cell batteries are mostly the kind you see every day. Those are actually, they're slightly different. They're alkaline batteries, but let me explain, what the reactions are and how they're set up. So at the anode, you generally have zinc being oxidized. The zinc is actually the casing. So the inside of the casing is actually is reacting. So the cathode is a graphite rod going through the middle, and then the terminal is at the very top. Then the negative terminal is at the bottom for the anode. And the reduction that occurs is actually manganese plus 4, manganese oxide, react going to from a plus 4 state to a plus 3 state. So that's the reduction that's going on. And the electrolyte is this moist paste of magnesium oxide, manganese oxide and ammonium chloride. And ammonium chloride, remember, is an acidic salt. So that's the reaction that's going on. The cell voltage is about 1.5 volts. So that's this is not all that different from the voltaic cells we've seen, other than that the electrolyte is more of a paste. It's called a dry cell. It's still a paste, but it's not like an aqueous solution. It's a very dense paste with just a little bit of water in it. A little more common are alkaline dry cell batteries. And remember, the electrolyte of the acidic dry cell battery is an acidic salt. In this case, it's the same basic cell, except the electrolyte is alkaline, and it's potassium hydroxide paste. So the setup is pretty much the same, except the manganese oxide is in potassium hydroxide paste. And same thing, the zinc from the casing is oxidized at the anode, and the cathode, it's graphite, sometimes a brass rod. And that's a similar reaction for manganese being reduced, except it takes place in it's ammonium hydroxide. It's still reacting with ammonium in the solution, but there's ammonium hydroxide instead of ammonium chloride. Cell voltage of 1.54. The voltage differences are because of the different concentrations. It's the same basic oxidation reduction, but of course the concentrations will change, and so the voltage changes a little as well. A longer shelf life than acidic dry batteries. They're a little more chemically stable, longer working time, and the zinc doesn't corrode as much. The zinc corrodes a little more in acid, but it doesn't corrode as much in base. So these are sort of the workhorse batteries you see most of the time, Energizer. And all of them are the same basic idea, but you have a little different setups as to how everything is structured inside, concentrations. Those are the main differences. The basic reactions are the same. Lead storage batteries. These are the batteries that are usually in car batteries, and sometimes you can have external lead storage as well. So generally they're set up with 6 electrochemical cells in series, each producing somewhere between 2.05 to 2.1 volts for a total of 12 volts. One thing to remember about all these batteries is it says 1.5 volts, but that's pretty much like when you get the battery, it's at least 1.5 volts. Most things that are set up to run on these batteries actually can handle, most of these devices are set up to handle between 1.5 and 1.2 volts. They don't need, because as the battery, as things drain over time, as the morphology of the battery changes, you might get some things being corroded, and the voltage can drop a little bit. Even though it's the same reaction going on, just because the concentrations change, the voltage will drop a little over time, and the things you power the batteries with can handle that. So the same thing, we talk about a lead storage battery being 12 volts, but it's not exactly 12 volts. It probably starts at a little more than 12 volts, and everything that's powered by it expects that it'll be at least 12 volts, maybe a little bit more, maybe a little bit less over time. The electrolyte here is 30% sulfuric acid, so quite acidic. The anode is solid lead. So these are fairly toxic. You want to be very careful with your batteries because you've got this relatively toxic lead in there. So the anode, you get an oxidation of lead to lead sulfate, which is, you've got a lot of sulfuric acid there. So there's a lot of sulfate ions for the lead to interact with. And the cathode is lead coated with lead oxide, and it's the lead oxide that's reduced in this reaction. It needs acid to happen, which is great. There's a lot of H plus floating around. And so in this case, you get that converted to lead sulfate as well. So those are, those are the reactions that are happening. And so they're set up. So there's a lead grid and a finely divided spongy lead. So there's a lot of surface area. So you can get a lot of electrons going at a given time. Increasing the surface area doesn't change the voltage, but it does increase the current you can get out because you can get more electrons going through if there's more reaction sites for this to happen.